Hi guys, welcome back to Physics 145. Today we're going to look at chapter 4. Our chapter 4 will be talking about Newton's law of motion, right? So Newton's is the father of mechanics. He started everything in kinematics, dynamics, and so on. So we're going to look at all the fundamental law about Newton's, right? So Newton has three laws. Newton's first law talking about inertia, and then Newton's second law talking about the force, and then the Newton's third law about action and reaction. But before that, we need to look at the basic thing that you need to understand before we go into Newton's law. So the first part, number one, is inertia. Right? So what is inertia? Well, you have this experience before. If you are asked to push something, okay, small is very easy. And then if you are asked to push something huge, very massive, you feel like it's very difficult to push. Well, that experience was actually encountered by almost everyone. For example, you're pushing a car. Well, a car on a wheel with a handbrake release. So you feel that it's actually quite easy to push a car like ganjil or even motorbike. It's very easy because the mass is small. Okay, their mass is small. And then if you're asked to push a lorry, a 5-ton lorry, well, you are facing a difficulty because the mass of the lorries are huge, right? And that concept is related to something that we call inertia. So that means inertia is the intrinsic property of an object to resist, okay, the external effort to change its position or to change its situation. For example, an object that is already at rest, when you try to push it, you try to resist the external effort. So you feel that difficulty in pushing the object because the object try to remain stationary. Okay, and then another scenario is if the object is already moving at a constant velocity and you try to stop the object, or you are trying to change the direction of the object, you also feel the same difficulty because the inertia of the object. That means the object try to remain in its uniform velocities motion. Alright, so that is the inertia. So we write down the definition of inertia. So inertia is the characteristic, or we can say the habit, okay? The characteristic of an object to try to maintain its, okay, try to maintain its what we call that, current state of motion. So this states of motion refer to either stationary or moving with constant velocity. So that is the meaning of inertia. So how do we measure inertia? Inertia is measured by the mass. Okay, inertia is measured by the mass. Okay, inertia is measured by the mass. So that means mass is the quantitative measurement of inertia. Alright, so that means the larger the mass, it means that the inertia of the object is large as well. Okay, so the opposite is also true. The smaller the mass, the smaller the inertia. So that is the meaning of the mass. So the unit of mass, as you know in our first chapter, is measured by the kilogram in our SI unit. Okay, so that is a basic thing under Newton's law of motion. So the next one is momentum. You already know the concept of mass, and then previous chapter number 3 you already learned the concept of velocity. So now we look at this momentum. Sorry, this one changed to 4.1.1. This is 4.1.2. So now the next one is the concept of momentum. So our concept of momentum is this. Momentum, the symbol P is defined to be the product of mass and velocity. Okay, velocity, not speed. So that means momentum is equal to mass multiplied by velocity. But since your velocity is a vector, your momentum is also a vector. Alright. So the unit for momentum is equal to the unit of mass, which is kilogram, multiplied by the velocity. Alright. So that is one of it. But also, sometimes we can use this, Newton second. Okay, Newton second. You know that Newton is kilogram meter per second per second. You multiply by the second, so you end up with the same unit here, kilogram meter per second. Alright. So Newton second is also the mass, kilogram meter per second is also the units. Alright. So both can be used in your exam. Alright. So that is the momentum. Now these two things is a foundation for the law of Newton's the Newton's law of motion. Alright. So after this we look at the law of motion, the first law. Okay, the first law. So our first law, right, this is now 4.2. So we call this one Newton's first law. Okay, it's actually Newton's first law of motion, but it's understood that we just simply write Newton's first law. So we had to define Newton's first law first. Okay, so definition is this. Newton's first law states that any object, okay, any object will maintain its original state of motion, okay, if no external net force applied to it. Okay, if no external net force applied to it. So our original state of motion here, what is the meaning of original state of motion? Original state of motion can have two possibilities. Number one is stationary, and number two is constant velocity. Okay, constant velocity. For example, we bring the case to outer space, so that is we are not under the influence of any gravitational force. So if you are not moving relative to any astronomical object, okay, star, planet, and so on, you are stationary, totally not moving at all. So that means you'll be forever like that. Okay, if no external force applied to you, no asteroid strike you, you are not pulled by any black holes, you are not firing your rocket, your thruster, and so on. Okay, you don't throw anything out of your spaceship, right? So you'll be staying like that forever. Okay, I mean forever. And if you are moving with constant velocity, you'll be doing that forever as well, if you don't have any external net force. So that is the meaning of original state of motion. So if you are stationary, then you'll be forever stationary. If you are constant velocity, you'll be forever constant velocity. Okay, to clarify here, constant velocity means, because velocity is a vector, that means if you are moving in a straight line in outer space without the influence of any gravitational object, then you'll be forever doing that. You'll be moving in straight line. You don't have to worry you will going to change direction, because you'll be forever doing that. Alright, so that is the meaning of original state of motion. But condition is no external net force. Okay, no external net force applied to it. Now that is our Newton's first law. So the example will be just discussed just now. Object in outer space, stationary, and also in constant velocity. Okay. Well, it sounds like very easy to achieve that type of experiment, but when you go to outer space, well, actually you are not free from anything. You are free. You are not even free from like gravitational force. Everywhere you go in the universe, you are subjected to either very small gravitational force or very strong gravitational force. Even between the empty space between galaxy, from galaxy to other galaxy, those distance you're talking about millions of light years. But even when you are between them, you still feel the force, but the force are very minute, very small. And when you talk about near a black hole, if you are watching the Interstellar movie, that force is strong. The gravitational force are so strong that it can even influence your time, because your space-time already changed. Okay, your space-time are curved. That is what happened to you when you go to outer space. Actually, when you talk about not under any influence, well, it's not entirely true. It's quite difficult to find a place with no influence at all. Okay, so that is Newton's first law. All right. So now, the next one is our Newton's second law. Okay, Newton's second law, 4.3. Okay, so Newton's second law is the most famous one because it involves the formula that you are very familiar with, which is the F equal to ma. But before that, before you reach F equal to ma, you need to know something else as well. So Newton's first law states that, okay, states that Newton's second law states that the net force is directly proportional to the rate of change of momentum. All right, so our net force, F, net force, some books using this one, net force, but in our case here, it's understood that we just write F. That is good enough to use F. Is directly proportional to the rate of change of momentum. Well, in actual case, it's written like this, but for your case, you can actually assume something like that also. Okay, something like that. But I'll prefer to use this one because later on you're going to do something like our calculus. You already learned calculus in Form 5. Okay, so you should have mathematics pass calculus in your additional maths, or else you won't enter FSG here. So now from here we put in a constant k, okay, dp dt. So this constant k is equal to 1 simply because F is defined in Newton. Okay, so to define in Newton, so it means that 1 Newton is equal to the force that is enough to accelerate 1 kilogram per object by 1 meter per second per second. That one was defined by Newton's long time ago, okay, about 400-500 years ago. So that's why our k is 1, so we end up with F equal to dp dt. So that is the original equation for Newton's second law. All right, so now our law here, it don't look like F equal to ma because we haven't differentiated the equation yet. So now we're going to differentiate this equation. So our F is equal to dp dt, but we know that our P is equal to mv according to our definition here, momentum. Okay, momentum. So when you differentiate a two variable like this, you have m dv dt plus v dm dt. So this one is the rate of change of velocity, and it's going to end up acceleration. Okay, a equal to dv dt plus v dm dt. This one is the rate of change of mass. So when do we use this equation? This one is mostly used in a system which we produce force by throwing a lot of mass. For example, rocket. Okay, rocket, you burn gas and then push them out at high velocity with a lot of gas being thrown out. So that's why it is called rocket equation. Okay, this is called rocket equation. But not all systems behave like that. Like for example, your car moving not because you throw mass. Yes, of course you throw mass, exhaust, but the exhaust is not the one that push your car. If you are depending on your exhaust to push your car forward, well, to move from UiTM to Tabuan Jaya, it take you forever to reach there. Okay, sorry to tell you about that story lah. All right, so car is not depending on DMDT, okay, but it is depending on other system. Okay, yes, we lost mass, but we burn the petrol, we cause explosion. The energy is actually used to push the piston downward, rotary motion, change to linear motion. That is how your car moves. Alright, not like rocket. Unless you want to install a rocket on your car, so it might take you only a few seconds to reach Tabuan Jaya from Samarahan. Alright, and then you better think of how to stop your car by the time you reach the traffic light of Samarahan. Okay, sorry, not Tabuan Jaya. Alright, okay, so now that means our force is depending on two terms here: the mass with acceleration, and also the velocity multiplied by the rate of change of mass. But if the rate of change of mass is equal to 0, we can simplify the equation further. Our F become ma. So that means this is a special case for Newton's second law. Okay, it's a special case which we use this one most of the time. Okay, most of the time. I don't think you'll be using this VDMDT in your syllabus, because that one is for a higher level. Okay, for a higher level. Unless you are in a rocket science faculty, maybe you need that lah. I think you definitely need that. But in your case, you only need F equal to ma. Alright. So that is how we get the F equation. So you cannot define Newton's second law straight away by saying that Newton's second law states that F equal to ma. That is totally wrong. You have to state this one. Okay, rate of directly proportional to the rate of change of momentum. And finally, from here you can have this one. All right, and then this one, it actually provide us the foundation for another category of things. Now, you already learned acceleration, right? And you know that acceleration is equal to v minus u over t. So if we put this one in, we're going to have F equal to mv minus u over t, and then F, this one is mv minus mu over t, and we will change the t, we move the t over to this side, ft, and this one is mv minus mu. If you look at this one, this is final momentum, this is initial momentum. So this one is final minus initial. So we end up with something like this. Ft is equal to change in momentum. Now, what is this actually? This one is called Ft or delta P. They are impulse. Okay, they are impulse. So that means impulse is equal to force multiplied by time, or impulse is equal to change in momentum. The symbol for impulse is I. Alright, so that is another thing, impulse. Okay, but I don't see impulse in the syllabus, but it's good to know there are something like that. Alright, okay, next one. Okay, next one, we will look at example later on. Okay, so our next one is our Newton's third law. Okay, our Newton's third law. That is 4.4. Okay, Newton's third law. Well, Newton's third law is states that every action normally is a force that you apply. So every action will have an equal but opposite reaction. Okay, opposite reaction. Okay, so that means whatever you do when you apply a force, there's always an opposite side of the system. Okay, so for example, you press on the table, you can feel actually the hardness of the table is simply because the table push you back. All right, so that is the meaning of the Newton's third law. All right, every action will have an equal. That means the reaction have the same magnitude as the action, but they are in opposite direction. For example, okay, this one we look at a few examples. Okay, so you are standing on the ground. Okay, that is you. When you are standing on the ground, you experience a force. Okay, your force is the weight. Okay, your weight W equal to mg, and then you have an reaction. The reaction is from the floor, from both your feet. Okay, but we only draw one. This one is the normal reaction. Okay, because it is 90 degrees from the surface. Your force, your weight is also 90 degrees relative to the surface. So these two forces are the same. Okay, W is the action, normal reaction is the reaction. So the magnitude of your normal reaction is equal to the magnitude of your weight, which is equal to mg. But they are in opposite direction. Okay, they are totally in the opposite direction. All right. So that is one example. Another example is when you are pulling something. For example, a trailer. Okay, a trailer with a wheel, so that we don't have friction. And then with a tractor. Okay, a tractor, you know, that have a gigantic wheel behind there. Okay, small wheel in front, this gigantic wheel. So when you are pulling something, your tractor is pulling. Okay, so pulling is in this direction. This is the pulling force. Okay, pulling force. But because of the action reaction, Newton's third law, so the tractor pull back with the same pulling force, but it is negative. Okay, they are the same because the force in the rod or in the change is that we in on the same line. Okay, but in the opposite direction. Okay, so that is another one of the example about action and reaction. Sorry, I should have used a blue color here. Okay, so this is our blue color force. All right. So these are example of action and reaction. All right, there are a lot more example. Okay, there are a lot more example on these type of things. All right, so that is Newton's third law. All right, now the next one is the application of Newton's law. All right, application of Newton's law. That is 4.5. Application of Newton's laws. Okay, Newton's law. So application of Newton's law is we compile all the law and then we use it in every scenario that we can imagine. So before that, we want to talk about something that is called free body diagram. Okay, a free body diagram. What is a free body diagram? Okay, so a free body diagram is a simplified diagram. All right, simplified diagram a simplified diagram to show, okay, to show the action. Okay, to show the action, that's it, to show the action and reaction possible. Okay, to action and reaction. So for example, when you say something like a human standing on the floor like this one, normally if you want people to be understand more, you normally draw a human figures and then the floor and so on. But example number one, I can actually replace this one by simply an object like this. Humans, I assume this is human. All right, the human have a weight. Human have a weight. This is the weight W, and then there is a reaction from the floor. The reaction from the floor. So this is the reaction. So I can simplify like this so that I don't have to draw the human figure shape. Alright, so it simplify the way in the to tell the story in the action and reaction. Okay, number two. Okay, number two. So when you talk about a car moving uphill, so just simply draw something like this. A car moving uphill. So there's a box, then simply a box, maybe with a wheel like this, and then you tell the story about action. Okay, the force from the engine, and then the friction possible. Okay, the friction from the floor, and also the other forces. Okay, other forces from the car itself. Alright, so these are examples, simplified version. You're not going to draw the detail of the car, the seat, the bumper, the windscreen, the light, the tire, the brand of the tire, Dunlop, and so on it. Okay, so this is the meaning of the free body diagram. Sometimes we even simplify those things in even smaller dimension. Okay, you can actually use a dot to represent a human, just simply a dot, and then the force is through the same point. Alright, and then the car maybe just a simple box without any tire, so you can assume that there's a car. So that is how we solve problem in physics. From the question, we actually change it into a simplified diagram, this type of free body diagram. Free body diagram, free of the body. Okay, free body diagram. Alright, so this is the meaning of free body diagram. So now we're going to look at application. The first application, the first application in this our Newton's law. So our first one, A. Okay, so this one is in horizontal surface. Okay, horizontal surface. Right, now our horizontal surface is object that is on a horizontal surface. For example, a box. Okay, a box that had been pulled by a force. Okay, by a force F. Okay, and then it experiences maybe friction on the floor between the object and the floor. Alright, so you are asked to calculate, let's say, what is the acceleration of the object. So for example, these are just example lah. Okay, so this is on horizontal surface. Sometimes we don't have any friction. This is one example. Another example will be you pull something. Okay, you pull a box. Okay, you pull a box with a force F, and then this box is pulling another box. Okay, pulling another box from a string. And then to make things become even more complicated, this one has friction, this one also has friction. I call this one F1, this is F2. Alright, and then there are tension in the string. Okay, tension we call T, and you are given the mass. Okay, the mass, this is M1, this is M2, this is M, and you are asked to find their acceleration, for example, in both cases. Alright, so that is horizontal motion. Okay, horizontal motion. Other than this, we can also have a horizontal motion, not only pulling. We can have a horizontal motion that is talking about pushing. Okay, you push something with a certain force, okay, and see what happened to it. You push, okay, you push the object with a force F. This one is mass M1, this is mass M2, and both of them experience different friction. This is F1, this one is F2, and then they might be accelerating with an acceleration A. Alright, so this is actually quite the same. This one, M2, is being moved forward because of the tension in the string, action reaction. This one is actually quite the same. When you push box M1, the box M1 will push the box M2. We call this force here force F12, from M1 pushing M2. That is the action. And then because of reaction, the box M2 will push back with a force F21. These two forces have the same magnitude, but they are opposite, totally opposite. So these are example of pushing system. Okay, this one is pulling system. Okay, so these are example of things that move in horizontal. Sometimes friction is not there. They are because the surface are smooth. Sometimes the friction is there. All right. Now the next one will be B. Okay, the next one will be B, inclined surface. Okay, inclined surface. Inclined surface, that means a surface that is tilted at a certain angle. Okay, for example, a surface that is like that, then you move up at a certain angle, that is called incline. So incline simplify to be something like this. Okay, this is a floor. Okay, this is a floor. You have a board, okay, or just simply something flat surface. You push it up to a certain angle. This is theta. This angle is called incline angle. Okay, this is called incline angle. All right, incline angle, and this is an inclined surface. Okay, this is the inclined surface. Okay, and then the inclined surface can be smooth, or number 2, rough. Okay, rough. So smooth, no friction. Rough, you have friction. And then you put something on top. Okay, you put some object on top of the surface. Okay, and then you observe what happened to the object with a mass M. All right. Now inclined surface problem will have more difficulty to solve it, because this deal with component. Okay, because the weight is downwards, and then the vector of the weight can be split into 2 components. Okay, now we are going to look at how we are going to resolve the vector, how we split the vector of the weight into 2 components. All right, so now we simplify. We don't draw something like this. We just simply draw an inclined surface, just like that. Okay, like this. Okay, that's it. And then an object here. And then we have an object here. This is our object. And at the moment, we assume the surface is smooth. Okay, smooth surface, so we don't have to worry about friction. Now we draw our weight. Okay, our weight is downwards. This is our weight from the center here. Our weight. This is our weight here. Okay, here I can see that. There is our weight. W equal to mg. Now assume again the incline angle is theta. Now from vector, we know that we can split this vector W into 2 components. One component is parallel with the surface. Okay, parallel with the surface here. And then another one will be perpendicular to the surface, like this. Okay, perpendicular to the surface. So now from this geometry, we know that this one is also theta. All right, so now how we split that one? We draw another parallel line from here and also here, so that we can draw the next vector. Our first vector is the one that splitted to this direction. See that? Okay, so that is the component of the weight parallel with the surface. We call this one W parallel. Okay, and then the next one is this component. Okay, so this component is a component that is perpendicular to the surface. Right, perpendicular to the surface, and we call this one W perpendicular. Okay, W perpendicular. Now the next thing is, how are we going to get the formula for both of them? Okay, so this one W parallel is given by this W sine theta, or mg, because W is equal to mg, right? So it become mg sine theta. The same thing for the perpendicular, W cosine theta, or mg cosine theta. So these two formula you have to remember. Okay. Well, remember is a good thing lah. Normally I'll prefer if you can memorize it, but I even prefer if you know how to get that formula. Alright, so that is for inclined surface. Alright, that's it. The theory for this one, for Newton's law, and the application is either this one or this one. Alright, so we are going to come to the next one. We look at example. Our example are all in 4.6. Okay, so this is our patch 1. This is our patch 2. Alright. Okay, come to the next one now. Okay, our 4.6, or you just simply go to example. Example 1 on Newton's law. Okay, we subdivide this one into 4 lines so that I can have more space for each example. Yeah, don't want to waste my paper lah now. Supposed to be online. I use more paper than before. Okay, example 1. Let's say we have an object. Okay, and then this object is on a horizontal surface, and then you apply a force F of 20 Newton. The object has a mass of 0.50 kilogram. Okay, now calculate the acceleration of the object or the block if A, the surface is smooth, B, the surface has friction, F is equal to 4 newtons. Okay, so that's it. That's example 1. Okay, solve example 1. Let's solve example 1. So I might use a red color. Sorry, I don't have red color pen here, but this one is like too difficult to write. Okay, never mind. We just go on with this one. Maybe I use a darker color. This is the same. 6B. Maybe this is good enough. 6B. Alright. So our first one, A. Okay, A. So our first one, A, is we are going to use the Newton's second law special case. F is equal to ma. So our force is 20 only because there's no friction. So our force is 20 equal to the mass of 0.50 A. So A is 20 divided by this one, right? The force is a big, right? 20 Newton. So 20 Newton divided by this one, right? So 20 divided by 0.5, huge value, 40. Okay, we have 40 meter per second per second. Okay, F equal to ma, 20 Newton over 0.5, you got 40 meter per second per second. So that is huge. Acceleration is huge. Alright, and then example number number B. The surface now has a friction. Now our object, same object, we have a force F of 20 Newton with a friction of 4 Newton, and the mass is still the same. Okay, but the friction is in opposite direction. So when you use Newton's second law, F equal to ma, remember this is a net force. The net force means the force in front. Okay, the force in front. Maybe I change the symbol. This is F prime. So this one we slot in one more. F prime equal to ma. So these are F prime. This is the F. So we have F prime minus F is equal to ma. Now you see you minus the friction because in opposite direction, right? So we see 20 minus 4 equal to 0.5a. So our a will be different now, definitely smaller. So we have 16 divided by 0.5. So we have 32 only. Okay, 32 meter per second per second. So that means when you have friction, friction actually slow things down. Okay, it don't allow you to, not to say slow things down, it reduces your acceleration. Okay, so you see our force here, this calculation is very straightforward because our force is also parallel with the surface. Now our example 2, example 2 will be when the force is not parallel with the surface. Okay, so our object is here. Now our force is actually something like this now, F. Okay, so our force here, okay, I will give it some value. The force now is, let's say, 10 Newton, and the angle here, theta, is 30 degree. Okay, 30 degree. All right, so the mass for the object, mass is equal to 2 kg. Okay, 2 kg. All right, so same thing. Okay, we only need to calculate the acceleration of the object A. But given that the object experience a force, a new what we call this, the frictional force of let's say 5 Newton. Okay, 5 Newton. See whether the object can move or not. All right, now this calculate A. Okay, calculate A. So we are going to use the same thing, except our force here, we have to split it into two components. But in this case, object is moving on a horizontal surface. Okay, horizontal surface. So we need to take the horizontal component. Okay, we're going to take this component. Okay, the horizontal component. This one here, the red color component. Okay, so I will call this one Fx. Okay, Fx. All right. So Fx, how do we get Fx? So our Fx is equal to F cosine theta. So it will be 10 cosine 30 degree. Alright, so our answer should be 8 point something, 8.6 I believe. 10 times cosine 30. Okay, so answer, okay, answer is this one, 8.66. Okay, 8.66 Newton. That is our horizontal component. We can only use this one to calculate the acceleration because the object moved not in this direction but horizontal. So our formula is F equal to ma. So we are going to use now is 10 Fx minus friction is equal to ma. So this one already calculated, 8.66 minus 5 Newton is equal to 2a. So our A will be 8.66 minus 5 divided by 2. We got 1.83 meter per second per second. Okay, so these are examples that involve forces that is not parallel. Okay, forces that is not parallel. Okay, next one, we come to inclined plane. Okay, inclined plane. Example 3. Okay, example 3, inclined plane. We have an object here. Okay, and the angle here, theta, is 40 degree. The mass of the object is, let's say, 10 kg, very massive object. And the distance from the object here, I call this one distance is equal to, let's say, 3 meter. 3 meter. Okay, and the surface is there are two possibilities later. Okay, so this is a surface on incline. Now calculate two things here. Okay, calculate the velocity of the block, calculate the velocity of the block at the base of the inclined plane, okay, inclined plane, and the time, okay, the time to reach the base if A, the surface is smooth, B, the surface is rough, that means with a friction of, let's say, 4 Newton. Friction of 4 Newton. Alright? Okay. That is a difficult one. That is a difficult question. So what do we do in the first place? The first place, what we do is, to calculate acceleration, you need to know the, to calculate the final velocity, you need to calculate the acceleration. To get the acceleration, you need to find the force. Since there is no other force here, in this case, in the first scenario, is that you only have a force like this. Okay, where is the diagram just now? Okay, this force. You need to calculate this force, W parallel. Okay, W parallel. So our W parallel is this one, mg sine theta. So you have to remember that formula. So mg sine theta. But before that, we simplify that diagram. Okay, for A. Okay, we have this object, and this object is experiencing a force, okay, a force of W parallel. So we calculate the W parallel first. Okay, the mass is 10 kg, the angle theta is 40 degree. So our W parallel is mg sine theta, which is 10 times our g, 9.81, and then multiply